Okay, everybody. So consider this map from R2 to R3, F, given by this formula. So here we see that that's R2. And we have 1, 2, 3 component functions. So the output is, in fact, correctly R3. Okay, so this is about derivatives. So just to get it out of the way, if we take the partial derivative with respect to x1 variable, and we do it to all 3 component functions, then we get the first column of the Jacobian. So what I will do is, I guess, 6x1. I have 2 more formulas. Derivative with x1 gives a 2x2. One more formula, derivative with x1 just gives x2 to the third. This is the x2 variable raised to the third power. Okay, and the second column, because there's 2 input variables, there are 2 columns, 2 velocities. And okay, so derivative with respect to x2 now gets applied to each of these, and that'll give me another vector with 3 things. Okay, what are those 3 things? Okay, now at the point P equals -1, 2, that means that x1 becomes -1 and x2 becomes 2. Okay, well then, what do these things become? Let's give ourselves some more room. At P equals -1, 2. Oh, -6. I think that's correct. Okay, and so what we'll see is that actually these 2 now specific vectors are actually going to be equal to the derivative of f at the point P applied to the vector 1, 0, which is sometimes called I hat or sometimes called E1. And that's actually what that vector is. And this vector over here is the derivative of f at the point P in the direction of the other basis vector, j hat, 0, 1, or E2. Okay. And those are the velocities of 2 curves, as we've seen before. But now, what is dfp of v when v is some other vector, some other movement vector that's not just a movement in x alone, and not only a movement in x2 alone, but it moves in both at once? Well, what do we do with vectors? We do linear combinations. So what we're going to do is just take one of this. So I guess maybe I'll just 1 plus 1, essentially. Copy, paste. I'll get rid of the and. What we're going to do is v has 2 components, and so we'll do 1 plus 1. And now this is a linear combination. If v was 3, -2, we would take 3 of this first vector plus -2 of this second vector, right? And we'd get some vector. We do the linear combination, and we get some vector. What was it? -18, 16, 48. And that would be dfp of v if v equals 3, -2. Okay, So we just sort of linearly combine. And so I'm going to explain this better now. How would you actually answer this question? Okay, so consider the map given by this formula. And this is in blue, so it could change on the quiz, but not much. Part A, what is the derivative? Okay, so I need to use words, pictures, and formulas. What is the derivative dfp at p equals that? Well, first of all, I have to say what it is. The derivative is a linear map. Okay? And I need to say what linear map? What linear map? Well, because it's at the point p equals -1, 2, we plug in that value to these velocity vectors, and we get two actual vectors. And we just, well, it's a linear map, linear combination. So now I switch to formulas color. df sub p, or dfp, has the same input space and the same output space. But what does it do? It takes a vector, v1, v2, and it sends it to a linear combination, v1 of -6, 4, 8, plus v2 of 0, -2, -12. And you see, this depended on the point. We had to linearize at the point P because that's where we want it to make sense. Like nearby to P, this is going to be a good formula. And so that's why we plug in for P. For, x1 becomes -1, and the x2s become a 2. x1 becomes a -1, that's how we get there. x2s become a 2, and etc. And so this would be a completely different pair of vectors that we're linearly combining if we chose a different point. Okay. But that's it. We just wrote down we said the derivative is a linear map, and we wrote down the formula for that linear map. We still need picture, but I'm going to put that to the end. Let's do part B. What is dfp applied to the vector v, applied to the input vector v, when v is 1, 1? When v is 1, 1. Okay, well, we just use v equals 1, 1 as coefficients in the linear combination. Up there. And so I can literally just put a 1 there. That's an 8. And a 1 there. And you note that this thing here, df sub p applied to v, is a vector. It's -6 to -4. It's a vector now. So df sub p, not applied to anything, is a map. It's an entire map. But then we can plug in to a map. So let's plug in the vector 1, 1. And then we get an output, which is actually a vector. Okay. Excellent. We have words, we have formulas. Where are the pictures? Okay, so this picture, I need the point -1, 2. Okay, I can actually pretty much do that point, so let's go to our input space. -1, 2 is maybe here. That's p equals -1, 2. Okay. And then our output space, I don't know, I'm just going to make this like gray. And now our output space, has to be three-dimensional, okay. So now I don't really exactly know where f of p is. I could plug in -1 and 2 and get 3 actual numbers, and then I would know exactly where it is in 3 dimensions, like on my computer. But I don't really need that, so I'll just sort of make up a spot for it. Maybe it's here. Maybe that's f of p. I'll put the label a little bit farther away. Okay. So there's p and there's f of p. But now we need the derivative, we need this vector v, we need, what are these columns? Where do these, the columns of the Jacobian, where do they appear? Okay, and so what we do is now DFP is a new linear map, and what we want to think of it is we want to think that there's a new coordinate system based at P. This is like the V1, V2 coordinate system. And then there's a new coordinate system based at f of p for the outputs of this linear map. That's what we're thinking. But anyway, so what happens here is that if we plug in the point, well, let's draw one of our favorite vectors. How about in pink? It's this vector, 1, 0. Okay. If I plug in a 1 here and a 0 here, I just get that first Jacobian column, the partial x1, the velocity of that first horizontal curve, right? That makes sense. This is the horizontal curve. And so somewhere I will get this vector. And that is literally that column, -6, 4, 8. I'm not drawing it perfectly, obviously, but this is DFP applied to E1. Okay. And now there's another special vector. Let's draw it in green. This one, it's the vector 0, 1, or E2. Where does it go? Well, if I plug in 0 here and 1 there, I just get the second vector, the partial x2, the second velocity, which is a vertical velocity, I guess. And that goes somewhere. Notice I'm deliberately not, this is not 90 degrees. This was 90 degrees here, but it may not be over here. DFP applied to E2, it's just that second vector. Okay. It's just that vector when we plugged in, that one. Okay, and now where's V? I need to draw a picture somehow. This needs to get in there. Where's one? So I have these are in my picture. P is in my picture. F of P is in my picture. What about V equals 1, 1? Well, let's draw that in purple. That's the vector 1, 1. So, it's the tip of this little square here. Now, where does it go? Well, by linearity, it has to go to a linear combination of these two, which means it is the tip of this parallelogram. That is the vector DFP of V, where, this is V equals 1, 1. And we computed it before. We just did the linear combination with a 1 and a 1, and we get this one. Which, you see, you move in the red and then the green. You move the red, then the green, and you get there. Or you can move in the green and then the red. You move in the green and then the red, and you get there. And so this is how linear maps work. -6, 2, -4. Okay? And so what happens here, and we'll see this in integration, this entire little unit square of volume 1 gets stretched out to a parallelogram that has some volume, which we will compute as the square root of the determinant of the gram matrix of the columns of the Jacobian. But that will be later in the semester. Okay, and that will be the volume of this parallelogram. I don't know how to spell parallelogram. So this is just a preview of the future. Let's get rid of it. Oh my gosh, so many undos. Okay. And that's our picture. The derivative is a linear map. You write down the formula for that map. When we plug in a vector, we just take a linear combination. That is a linear map, is just linear combined vectors. And then we have to really think and be able to draw this. This is what's going to allow us, like this type of understanding, to see how all these formulas and words actually come into a picture in our mind. This is the type of thing that will allow us to use the formulas to, you know, win competitions in data science and to discover new science and new mathematics, and to really just to do computer graphics and do video games. You really need to be able to draw pictures like this.